So first part, pi is 180 degrees, right? That means a straight angle here. It says the electric dipole when placed in the electric field E. So let's say the electric field E is somehow this. Will have a minimum potential and direction of dipole makes the following angle with E, the positive direction of dipole. Okay, so let's say our dipole is something like, okay, let's say that dipole is something like this. That's our positive end, another is negative end. So in which direction the electric field would be minimum? Sorry, what is mentioned here? Potential energy would be minimum. So potential energy depends on dipole and its orientation with electric field. So first, let's consider this orientation. Consider the electric field throughout the screen like this, going into x direction. Let's consider the dipole like this, positive, negative. Obviously this will tend to rotate the dipole in somehow, it has some torque. So another way, if means this is for pi by 2, another is 3 pi by 2, it will have the same orientation, just the opposite of it. It will be something like this. So again it has some torque, uh, electric field repelling the positive end and negative end here, something like this. So these two are equivalent, so obviously these two will not be the answer. Now let's consider 0. So 0 would be the same. If the positive direction of the dipole moment, that means what is the momentum of dipole moment? Direction of any dipole moment is from positive to negative or negative to positive. Can you try to answer this question? Direction of a dipole moment is from positive to negative or negative to positive? Yes, I have got one answer, that is negative to positive, and yes. So if for any 0 degrees, it would be something like this. And if we are considering 180 degrees, it would be something like this. Means this one is for pi and this one is for 0. So which would have the least electrostatic potential energy here? So considering this here, the electrostatic potential energy can be considered this way. Which is more stable? The stable, if the electrostatic potential energy of some form is lower than the other, it in electrostatic sense it is more stable. Suppose जब हम gravitation की बात करते हैं, which point is more stable, this one or this one? This one have more gravitational potential energy, so definitely this is not as stable as this one, because this has lower potential energy. If it is allowed to fall, it will not fall with much speed, while this will fall at very high speed as compared to this one. In similar ways, if position 1 is lower in by than position 2 in terms of electrostatic potential energy, we would say that part is more stable. So try to consider and try to figure out which part is more stable here. Yeah, I see. One doubt is about what about the concept and chapter explanation. So obviously, this is a kind of revision part. We would not be in a position to sort out the whole chapter in a single session, but obviously, you can go on and find out videos, Toppr videos that we have already prepared on electrostatics. That will give you quite depth knowledge of electrostatics and other chapters also. So basically for this part we are discussing numericals and the concepts along with that. Okay, uh, I had a question that okay, someone is answering already. Okay, and the answer they are saying is A, because since if this is more sorry, if the electric charge is in the direction of, say this one is positive and this one is negative, in the electric field in this direction would attract this one towards this and repel this one, right? So that's why this is not stable and this one is much stable than that. This one is stable because in this electric field this would be attracted while this would be repelled. So the orientation will not be changing, there would be no torque at all. So that's why this is more stable. So this would also be having less potential energy. So our answer would be 0. Someone has tried and answered A. Well, you have tried nicely, but you missed one thing, that positive charge or the positive end of the dipole would get a torque away from the electric field. Okay, moving on to the next question. Let's read it together. A given charge is situated at certain distance from a dipole moment in end-to-end position experience a force F. If the distance of the charge is doubled, the force acting on the charge will be. Okay, let's try and work it out in a diagram. Let's say it's a positive charge. And it is at a distance from a dipole moment. Sorry, a dipole, not a dipole moment. distance of charge is doubled, the force acting on the charge will be. So, can anyone remind me the formula of electric field by by a dipole? Yeah, I'm waiting for your responses. You can put it on. Okay, I'm already getting the answers from you. So, the distance of the charge is doubled. You know that for a dipole, the electric field is directly proportional to the distance. Uh, sorry. If the distance of the charge is doubled, the force acting. Okay, let's try to bring it on to a level that something like this. This is a dipole. Let's consider a point at a distance r from it, say capital R. So, considering these two, this distance, the distance of dipole is quite smaller as compared to r. What would be the electric field at this point? Obviously, we can use the formula KQR here. So, for electric field by this force this charge here, positive charge, KQ by R plus L square, and by this would be negative, so KQ by R minus L. If we compare simply these, this would become out to be minus 2L by R minus L square, R square minus L square. Oh, sorry. So this is giving us KQ divided by R square minus L square, which we can ignore. The L part we can ignore because L is quite small as compared to R, and here we are getting R square minus L square the whole times A square minus B square minus A square plus B square minus 4AB, right? Oh, sorry, I wrote AB. We can for RL. So, if you're cancelling one R with this square, we would be getting minus 4 KQL by R. So, you see, the distance is getting doubled, and here we have got that the electric field, or obviously the force on a point charge because of this electric field, would be proportional to the inverse of r, that is the distance. So if the distance is getting doubled, the force would be halved or doubled. This is the case when force is getting doubled. This is the case where force is half. This is for 1/4. So you see, if it had been a case for a point charge, the electric force on this point charge, this different point charge here, a given charge, this charge would have simply get 1/4 because force is inversely proportional to the distance. Here, in case of the dipole, the electric field is getting uh, electric field is, or the resultant electric force is inversely proportional to R. So that's why if the distance is doubling, the force would be halved. So our answer would be B here, F by 2. Okay, so moving on to next question. Try to take your time and uh, get the get deep into the concept here. The electric potential at a point on the axis of an electric dipole depends on the distance r from of the point from the dipole as 1 by r, 1 by r square, 1 by r cube. So this is nothing but whatever we discussed earlier. Means electric potential at a point. We just discussed electric field by a point. So if you are considering an electric dipole and considering the electric sorry, the distance r from the point from the dipole, let's say this is how, this is the point P, and we are considering the electric potential at point P by this dipole of charges Q. The distance between dipoles is 2L. So what would that be? Let's say the electric field, the electric potential by this would be, say this is R, and the orientation distance from the potential from the dipole. Okay, one thing we have missed here, we have not considered the orientation of the dipole moment according to the distance. Say this is the point and our orientation is this. And this distance is what we are considering here. This distance r from the center of the dipole. In that, the potential energy because of this negative charge would be kq by r, obviously being negative, and this one by positive. So it's getting cancelled, right? But obviously we have this length 2L here. So we would be having R minus L and R plus L, right? Subtracting, we would be getting KQ, the whole 1 by R minus L plus. So this could have been in the opposite direction too. This could have been in this orientation as well. So considering this part where the negative dipole, the negative charge of the dipole is towards that point P. Okay, so we are getting 1 by R minus L by 1 plus R by L, or the vice versa, something like this. We will be getting 2KL by R minus L. Again, this L is quite small as compared to R. We'll be ignoring it, and so that's why our answer means this electrostatic potential here would be proportional to proportional to 1 by R, because you see this is nothing but related to the dipole moment, right? You can see that this is constant K. QL, 2QL is the dipole moment, and R. R would be the only variable here, so that's why it is related to 1 by R. Our answer is A. And I think some of you have already tried to answer. Yes, some of you has already tried to answer, and one of them has already got the right answer. So keep trying with me. Moving to the next question. The question says an electric dipole of moment P is placed in the position of stable equilibrium in a uniform electric field of intensity E. It is rotated through an angle theta from initial position. The potential energy of electric dipole in final position is, okay, again we have same situation here, an electric field somehow this, and our dipole is this, and suppose it has been rotated by an angle theta. Initially its potential energy at the most stable state would, this would be considered as zero. So this is the difference in potential energy, that is what we need to consider, right? So we can say that this is the potential energy, or this is the work done that we have to find out here. So try to find out this while, take your time, and I'll be discussing this to you. Okay. Okay, so I have tried to locate your answers, and you are quite divided in your responses. I see some of you have tried and answering C and D. So yeah, so one thing, uh, you could see that the work done is directly proportional to the cos of this cos of theta, the cos of this deviation. So if the you can simply deduce, compare these two three things here. So the the potential energy, is it decreasing with theta or increasing with theta? Obviously at theta 0 means the stable position already. If the theta is increasing, the electric field, suppose from 0 to pi, or sorry, 0 to pi by 2, getting to 0 to 90 degrees, the theta is increasing, so we can say that at a perpendicular state its electrostatic potential energy is also increasing. So let's consider this part. Cos theta, is it increasing at 0 or decreasing, increasing from 0 to 90 or decreasing? At 0 cos theta is 0, and at 90 it is, sorry, cos theta at 0 is 1 and 90 is 0, so 1 to 0 it is decreasing. Sin theta, obviously sine is not be considerable here, so we would not be considering this part. uh, PE cos theta, and that is some of the answers are related to that. So minus PE cos theta, is it right? Because if it is minus sign, it could be related to this. So these two are not deducible by this method, right? Because both are decreasing with the increase in theta. So if we are considering this part as 0, sorry, this part only, not the whole cos theta, this theta as 0, this would be 1, right? So that means 1 minus 1 PE, this would, this whole this whole expression at C becomes 0 when theta is considered to be 0 degree. We are considering D. If theta is 0, this value would be minus PE. So obviously this is, this is giving us the electrostatic potential here for a point, for a dipole. Therefore, in option D, we are getting the right answer. If we consider at 0 potential and 0 degree deviation and 90 degree deviation. So our answer is D, and some of us have already given the right answer. Yes. So D is the right answer. Moving on. An electric dipole is kept at non-uniform electric field. It experiences a force and a torque, a force but not a torque, a force but not a torque but not a force, neither a force not a torque. So again, someone has already asked that, or said that, pointed that I'm not discussing the concept. So this is how we are discussing the concept. Uh, this is quite theoretical part. Consider again electric field and a dipole. And a dipole. Say, kept in non-uniform electric field. So this could be something like this, increasing or decreasing. So one way of showing non-uniform electric field is simply putting a point charge here. So obviously this is a radial, this gives radially outward electric field. So this is not non-uniform because electric fields are not parallel. So considering the force or torque because of this, it is kept in a non-uniform electric field. So first thing, if it is non-uniform, so at this the electric field is will not be same as the electric field at this thing, this end. So the force QE would not be equal to force QE dash, because E and E dash are not the same. So definitely these two are not cancelling out. Therefore, there would be a net force. Now consider the condition of torque. So if a dipole moment is getting, suppose this is getting force away from it, say F, and this one is F dash. If the forces F and F dash are same, that means the whole object is getting repelled or attracted with the same force. So there would be no uh, strain in this part, there will be no twisting occurring. So you can see that if you're putting an object something like this, you're moving up or down, you are exerting some force, but and if the force acting on the two ends are exactly the same, then there would not be a net torque. But if the forces are different, there would be a torque development and there would be some rotation. So that's how, if the forces on the two ends of this dipole are different, then there would be a torque, and that is what happening because QE and QE dash are not the same because electric field is not uniform. So a force and a torque, both. Option A is option A. Okay, someone has tried. So why do you think that there would not be a torque? Can you try to defend your answer? Someone has tried answer B. Well, we can discuss it in more detail, but for now, let's move on. Okay, again we have a question with dipole. We have so many questions with dipole this time. An electric dipole consisting of two opposite forces, each separated by a distance 3 centimeters, placed in an electric field. The maximum torque on the dipole would be. So, in which case the torque is maximum? The torque is maximum when the electric field is perpendicular to the orientation of the dipole. Something like this. So, QE, Q. And the torque would be QE times 2L. 2L being the whole distance. Now consider the charge here, 2 into 10 to the power minus 6 coulomb, and the distance to 3 centimeters, so we can write it 3 into 10 to the power minus 2 meter, placed in an electric field of 2 to the power 10 to the power 5 newtons. So here our electric field is 2 into 10 to the power 5. Now equate all the three things and we are getting our maximum torque, and maximum torque is nothing but dipole moment, this part, times the electric field. Dipole moment is 3 centimeter times this, that is what we are getting, 6 into 10 to the power minus 8 coulomb meter, and an electric field of 2 to the power 2 into 10 to the power 5 newtons per. That would be giving us 12 times 10 to the power minus 3 Newton meter. This is our torque, and let's see who have Okay. Situation A and B depending on the situation. I think that's the question. It is not uniform. The torque is said to be acting when the same force is acting on both ends. Positive direction. Ah, I just got a response about the torque and force concept. So let me try to explain this thing. So you have this object, say, forget for a moment that this is a dipole, just an object. If this point is pivoted, means you cannot move this part. You're acting, and this thing is open for exertion of force. So let's say I'm trying to put it with a thread. Some tension is acting in for upward direction, and some weight. The weight of this thing is acting from its middle. So the torque by this tension force, let's say the distance is r and this distance is r by 2. The torque by this force, this tension force, would be T times R, and torque by the gravitational force, say gravitational force be Fg, Fg times R by 2. So the same concept is being applied to a dipole. If one force is, suppose, if the two forces are equal, okay, so the whole mass of this dipole is getting pulled in one direction. But if one force is smaller or greater than the other, what is happening? One part is getting pulled while with greater force, another by less force. So the net force being the sum of the two forces, but there would be a torque because there is a difference between the forces acting on that part, and that would be a difference of the forces times the distance between the points of the where the forces are being exerted. So if the forces are different because the electric fields are different, then we will have a net torque in that direction. Yes, uh, I think that is how I would address that concern. And about this, we have just answered this as B, right? And yes, someone has already answered that correctly. Let's move on to the next question. So this time we have this question: a charge Q is placed at the center of line joining two equal charges, capital Q. The system of the three charges will be in equilibrium if small q is equal to. Okay. A charge Q is placed at the center of line joining two charges plus Q. So Q. Does this question tell us anything about the polarity or the sign of the charges? No. So let's forget that. And this one is the small q. The system of these three charges are supposed to be in equilibrium if q is to be equal to one of these. Means this is our option. And now consider in what situation would the three charges would be in equilibrium. So consider this charge. The force acting on this charge would be uh, same by this and opposite. That is why this will be stagnant at this point, right? So let's consider the force by this as F1 and force by this one as F2. Obviously F1 is minus F2, right? Because suppose this is F1, this is what F2 has to be in order to balance the two forces for it to be in equilibrium. So F1 is S2, so definitely this and this has opposite charges. So let's say Q is equal to some KQ, while uh, my K is some positive constant. Now consider if F1 is equal to F2 in magnitude, that means the force exerted by this small q charge is equal to the force exerted by the capital Q charge. So that means force is directly proportional to the charge and inversely proportional to the square of the distance. So we will see that F by R square, let's say this R, and this would be, it says at the center of line joining, right? So this would be 2R. So Q by 2R square. So can you say by that Q equals to minus 4 capital Q? Sorry, minus Q by 4. Yes, that is what how this situation is being solved and the equilibrium is being found. So can you try to find, and I think someone has tried to answer, and that is B. You're right about that. Let's move on. Okay, again we have something about theory. Let's read the question together. Inside a hollow charged spherical conductor, a potential is constant, varies directly with the distance from the center, varies inversely as the distance from the sphere, varies inversely as the square of the distance. So these are the parts where I would say you need to be very much. So this is a hollow sphere, right? We know that inside any hollow sphere, the electrostatic field or the intensity is always zero. But what about the potential? So this is the part you have to find out, and I would like you to take these as notes while we can discuss this in several other discussions, and take it as a homework. Now I will also be giving two new questions which you can take as a note and as a homework, which we will discuss in the next class. I'll try to have this in a recap part so that before moving to the next part of our discussion, we'll keep these questions and we'll try to answer that. Question number 9. This is a very nice question based on diagrams, and also some kind of some analysis is involved here. Try to take a note. I'll try to explain some part of it. ABC is an equilateral triangle, charge plus Q's placed at each corner, and electric intensity at O, O being the centroid of this part, O will be. So you need to find the electric intensity, or say the resultant electrostatic intensity, by these three charges. See, we have one thing that is purely not possible, because this is simply by one charge, but you can simply figure out the the possibilities here. If you try some uh, what do you call geometrical analysis, you can simply solve it very easily. Now the final question which I want you to consider as homework, this one. An electric charge Q is placed at the center at cube of side alpha. The electric flux on each of the faces will be. Okay, I think there should be some pictorial input here, but that was not available, so let me try and draw it for you. So suppose this is a Q and a charge Q is placed just at the center, and you need to find the flux through all the faces. So let's say this is one of the face, this is one of the faces here. So you can simply say that being at the center, this charge will distribute its flux through all the faces equally. That's one of the hint you can use here. And you also know that for a charge, whatever be the surface, the total flux would be Q by epsilon naught. I think you can work it out. This would be a very easy part for you. So let's wrap up our session here. We'll meet again. I hope you would have learned something in it, and you would have found some tricks that you could use in your examinations. Thank you for being with me.